Hypothesis testing. A researcher begins with a known population with a normal distribution with a mu of 500 and a standard deviation of 100. The researcher suspects that a particular treatment will produce a change in the scores for the individuals in the entire population. Because it's impossible to administer a treatment to the entire population, a sample of 64 individuals are randomly selected and the treatment is given to that sample. After receiving the treatment, the average score for the sample is 550. Although the experiment involves only a small treatment, the average score is enough that the researcher wants to hope to make general conclusions about the entire population. Okay, so let's work through this. So we know we have a population mu of 500 and an average for this sample size of 64 at 550. Well, the first thing we need to do is we need to find out is it a one-tailed test or a two-tailed test. And as I was reading that scenario, one word in particular should have stood out to you, and that was will produce a change. It could be a negative change, right? It could be a positive change. But all we know is that the researcher is hoping to see a change. So we're actually going to have two critical regions. We're going to have one over there on the lower side and one over there in the upper side. Okay, so we know that we're going to be running a two-tailed test. Now alpha is set at 0.05, but because it's a two-tailed test, we have to split that alpha. So 5% or 0.05 becomes 2.5% on this side, right? And 2.5% on this side. 2.5% is also 0.025, right? If you want to think of it like a decimal, that's going to help us when we find out the next step. And 0.025 on that side. Now again, if our z obtained falls somewhere in here, we have to fail to reject the null, right? So we're hoping that our z obtained falls somewhere over here or somewhere over here in these critical regions. But what's our cutoff, right? So again, the blue area right here is the body, right? Because it's the bigger part of the distribution. And over here in red is the tail, right? So we actually have two tails. So we're going to be looking in C, proportion in the tail. And we're going to go all the way down until we see 0.0250. All the way down there, which gives me a z of 1.96. So I'm actually going to have a negative 1.96 and a positive 1.96. So I have two critical regions. Okay, so the first thing I need to do now, or the next thing I need to do now, is find my standard error. Okay, so standard deviation divided by the square root of n. I have all these up here for the formulas. Okay, so standard deviation is 100, right, divided by the square root of our sample size of 64, right, which is 8. So my standard error is 12.5. I can then put that in my z formula, right, mean minus mu, divided by that 12.5, if you will, right? So 550 minus 500, right, for the population mu, divided by that 12.5, or 50 divided by 12.5. So my z obtained is going to be 4, positive 4. Right. So my z crit was positive or negative 1.96, and my z obtained is positive 4 with a standard error of 12.5. Okay, so now, so that would fall like right about here. All right, so my z obtained is positive 4. So that's good, right? I can reject the null hypothesis. That's my decision, right? That makes the decision happy, right? Researcher happy because their thing worked. This new therapy or treatment worked. And because that did, now we need to find out the effectiveness of it. So we have to find Cohen's d. And again, Cohen's d is mean minus mu divided by standard deviation. All right, this is effect size, right? So we would go let's see here, 550, right? 550 minus 500 divided by that 100, so 50 divided by 100. So my Cohen's d is 0.5, or a medium effect size. Right? So I would say yes, the treatment's effective. Our critical value as set by alpha 0.052 tail was 1.96, which gave us a z obtained of 4.0000 with a medium effect size of Cohen's d of 0.5.